Good morning, everybody. Welcome to our next seminar at the Machine Learning Needs Mathematical Optimization online seminar series. Today we have the pleasure of having Galit Shmueli, who is a distinguished professor at the National Tsinghua University in Taiwan. So she is the Institute Director of the Institute of Service Science. Galit has published in many different areas, including online auctions, count data, explain and predict. And she's very prolific. She has published in very top journals in our areas, such as Marketing Science, Management Science, Journal of the Royal Statistical Society, and she is also a fellow of the Institute of Mathematical Statistics, and she has been elected member of the International Statistical Institute. So for us, it's a great pleasure to have today Galit with us here, and we have accommodated a different time for her presentation, given that she comes from very far away. Thank you so much, Galit, for joining, and it's a pleasure to have you here. You have the floor. As I said, we usually leave the questions until the end, but if there is a very, very, very urgent question, I would check the chat. Thank you so much.
Thank you very much, Dolores. Thanks for the invitation. So I'm very delighted to give this talk here. I think this audience is probably quite different from a few other audiences that I presented this work. And this work is a little, I guess, unusual because it's, well, I'll say no more. You'll see it yourself. And I'm really curious to get as much feedback and questions and comments as I can from all of you. So the title of this talk is called Improving, in quotes, notice the quotes, those are very important, Improving Prediction of Human Behavior Using Behavior Modification. And sometimes people don't notice the quotes and then they think I'm actually teaching a new method to improve prediction. But what you're going to find now here is that this is actually a very dangerous strategy that I really don't advocate anybody using, but that actually might be happening. So let me start with an interesting quote by Yuval Noah Harari, who's a historian, and I'm pretty sure that you know of him or have read some of his books. He's written Sapiens, Homo Deus, and a bunch of other books. And in a more recent TED interview, he said the following. He said, "The ability to hack human beings means the ability to understand humans better than they understand themselves, which means being able to predict their choices, to manipulate their emotions, and to make decisions for them." And I highlighted these three things because this is what I'm going to focus on internet platforms that have the abilities to do all of these together. And that's something relatively new in the world, I guess, and especially for us academics in terms of analyzing and figuring out what is going on. So today's talk is going to follow, I'm going to give first a background. And in the background, I'll describe a little bit about how internet platforms predict user behavior and what they predict. And then I'll talk about how these same platforms can also modify user behavior. And with these two as background, I'm going to introduce my work, which is how this combination can lead you to, quote unquote, improve your predictions. And I'll show you how it might work. And then I'll show you how I bring in the statistical part, which requires new notation to put these two special things together in order to analyze its impact. And once I do that, I'll show you what the new notation is. I'll show you how I dissect the expected prediction error using this new notation. And once I do that, I'm able to uncover a bunch of pretty interesting discoveries. To me, they're alarming, but we'll see your reactions. Okay, so let me start. Internet platforms predict user behavior. What do I mean? Let's start by just I'm going to use the word behavioral big data a lot. So what do I mean? Big data, I think all of us are definitions, or we've seen them in different ways, but generally we're talking about data sets that have many records, typically from multiple sources. They're very rich, very detailed information about every record, and they're pretty much micro level. So that's big data, but you can have that on items, right, on inanimate objects. Then we have behavioral data, which is data about people. So this is people's measurable actions, reactions, interactions, very important, self-reported opinions, thoughts, feelings, everything that has to do with human behavior and interaction. And when we put these two together, we get behavioral big data. So we have these huge data sets with many records on many people, many users from multiple sources. They're very rich, very nuanced, also on interactions between people. So traditional companies such as, banks and supermarkets and insurance companies, they've been collecting this kind of behavioral big data for a very long time. They have a ton of information about each of their customers, where they go, what they do, what transaction. And they use it typically to predict future behaviors. So insurance companies will use this, for example, for pricing policies. Banks or credit cards companies will make decisions about giving you loans. Retailers will maybe use this for marketing. And what's new even for these guys is that the behavioral big data becomes more interesting, because now, for example, if you have any smart home devices, whether it's thermostats or robots cleaning the house, now they have a lot richer data and more nuanced data and a more behavioral data. So we have interactions between people in the house, who's coming where and when they're leaving, what they're doing, which heat they like. We move even closer to us. So inside our cars, now many insurance companies are requiring or requesting their customers to install little gadgets that measure not only where they are driving, but also how they're driving. Maybe you're accelerating very quickly when you're taking the turns. So now we have more information about how you're driving. Moving a little closer even to us, all the new smart wearables that track not only where we go, but how we go, who else we're meeting when we're doing that, and they connect with our apps and collect a lot of other physiological information and other information. If you're wearing any of the watches, the smart watches or the wristbands, of course, all that is collecting a ton of information about us. And even children now, right? The smart toys are collecting information about the children's behaviors, their interactions with the toys, maybe if there are other kids, siblings, friends, interactions with them as well. So basically now the traditional companies have much bigger behavioral data. And why do they want to collect this? Well, they want to use this for personalizing and improving their products and services. Some of them use it for fraud detection, for advertising, marketing, logistics, operations, lots of different reasons. So they collect the data and they're very valuable to them. What's kind of more new, not so new now as time moves so fast, is that internet platforms have started joining this game. So the internet platforms now collect a lot of behavioral big data, and they also use it to predict our future behavior. So if you're using any of these platforms, I don't know which browser you're using now, what computer you're using a tablet or a phone, or maybe you're using an Alexa or a Google Home, whatever you're using, any of these devices, any of the platforms. If you're streaming entertainment, if you're using shared economy, Ubers, buying on eBay, using Instagram, social media, doing online dating, anything that you're doing, these are what I call internet platforms. And they collect a ton of behavioral big data. Why do they collect it and predict our behavior? They're using this for the same reasons. They want to personalize. They want to improve their products and services. Some of them use it for fraud detection, advertising, we know is the biggest deal, marketing, logistics, and operation. So I'm sure this is not very new to you, but let me just start by saying they all have the capabilities to do these predictions. What kind of things do they predict? So here are classic things that they do. Purchase probability. What's the chance that you're going to purchase their product or their service? Churn probability. What's the probability that you'll be leaving their service? The third one, dwell time, or what's called time on site or time on app. They're going to try and predict how long you're going to stay on the app in this session, for example, or in the next 5 days or whatever it is. We know that many of these platforms can predict our emotional states. There have been several papers on that. And we know that they can also predict our voting intentions and even our voting behavior, whether we vote or not and who we vote for. And of course, there have also been several papers showing that they can predict our life events, things from pregnancies to changing jobs to anything that happens in our personal life. So these are the typical kinds of things that platforms can predict. And here's an example of a relatively recent prediction tool that Google sells to its advertisers. And you can see that what they sell are likely first-time 7-day purchasers. So they're going to try and sell the advertiser users who are very likely to buy that advertiser's product or service in the next 7 days. Or you can see churners. They want to help you find, if you're the advertiser, who's going to be leaving your service. So they're basically, Google is now selling these predictions to these third parties. And I'm going to be calling these third parties the customers of the platforms. So we have the platforms and we have their customers. And then we have the users who are us. So now that prediction becomes very important, let's just quickly look at how typically a data scientist, whether you're in machine learning or statistics or in a related field, how we typically build predictive models. So the typical statistical or machine learning approach is we're going to have a whole profile. That's the blue circle here, the user profile. And that's BBD if you want. And then in the green circle, we have the outcome that we're trying to predict. And we're going to try and build a model that links the blue and the green circles here. And once we have this model, this f of x, we will use this f of x to predict the behavior. That's the brown circle right here. And this distance between the predicted behavior and the actual behavior, the green and the brown, are what we call the prediction error. And of course, the prediction error, the prediction efforts are aimed at minimizing this prediction error so that our predictions are as close as possible to the actual observed behavior. How can we improve prediction? Well, one thing that we invest a lot in, people who develop methodology. Oh, someone's saying they're not seeing the slides. Dolores, can you see my slides?
I can see
I
them.
see the slides.
Yeah.
You have to double click on the little square down where
Yeah, David, you have to, you have to click, because at the moment you may only see the camera of somebody else. Yeah, but Galit, go ahead, because the slides are visible.
Okay, so let me take on from here. So as I said, we have this prediction task, and how do we try to improve prediction? Well, those of us who develop methodology, we try to improve this f of x. We try to develop better algorithms or better approaches, predictive models. We also try, another approach is to get better data. So if you have more accurate data, richer data, more predictive data, then you can improve your predictions. And we also know now, especially those who are using these heavy, let's say, deep learning types of models, their computing infrastructure is very important. So if you improve that computing infrastructure, that can also help you with your prediction efforts. And if you look at what companies are doing, what these platforms are doing, it's exactly in line with these efforts. So companies are hiring data scientists, paying them very well, and trying to grab the best ones. They improve their data they collect. They keep collecting more and more data. They purchase companies that have more data. So if you think about, you know, why Google would buy YouTube or Facebook would buy, you know, all these WhatsApp, it's because they get a lot richer data. And finally, these companies, you know that many of these platforms actually develop their own infrastructure. So Facebook has its own infrastructure, Amazon has its own, because those are really ways to improve predictions as well. Okay, so we talked about prediction, and let me now shift and talk about manipulation, or what's called, in a better way, behavior modification. So I'm going to claim, and I think this is not controversial, that internet platforms manipulate user behavior, and they have the capability to do that. What do? They're going to use these methodologies called behavior modification techniques that came out of behavioral psychology quite a while ago, and they're going to try and change users' behaviors. What kind of user behaviors are they trying to change? This is going to look familiar. The same things that they're trying to predict. So they might want to increase your probability of purchase, reduce your probability of leaving, of churn, increasing your dwell time, time on site or time on app, influencing your emotional state, pushing it towards this way or the other. We've also seen some nasty interventions in people's voting and also in their life events. So again, the internet platforms also use these behavior modification techniques for changing users' behaviors, and it's the same kind of users that we've seen before that are being predicted. What is behavior modification? As I said, these come originally out of behaviorist psychology. Here's an official definition. Behavior modification is an intervention designed to enhance certainty by altering causal processes that regulate behavior. In simple words, it means modifying a behavior in a predictable way. So the trick here is that it's modifying it in a predictable way. And you'll notice that we're talking about regulating behavior. This is really about manipulating your lower brain. So a lot of it is done without your awareness. There are now books by some are academics, some are practitioners who talk about using these techniques. So one example is a book by Nir Eyal called Hooked that say that companies must learn not only what compels users to click, but also what makes them tick. So he's talking about creating habits for users. Habits are defined as behaviors done with little or no conscious thought. So when we talk about this behavior modification, a lot of it is talking about unaware behaviors. And there's a whole host of behaviorist techniques. Anything from, there are techniques called tuning and nudging that introduce subliminal cues into your context. Things like herding and tunneling, which manipulate the context. So for example, if you enable notifications on your phone, for example, when the notification pops up, what you're going to do is you're going to click on that notification and it will take you directly to where it's supposed to be taking you. So they basically tunneled you right into the place that you're supposed to be going. Kind of similar to how Las Vegas uses techniques in order to herd people into the right places in their casinos. There's also a whole host of techniques that use conditioning, also called operant conditioning, coined by B.F. Skinner, the very well-known behavioral psychologist. And this has to do with reinforcement schedules. So for example, when we get random rewards, those are more addictive than if you get them on a fixed schedule. And all these very, very well-researched techniques that work very well are now being used very heavily by platforms. So as I said, these started out from psychology, and then the behavioral economists picked up on them and said, oh, this is very cool. Let's use these kinds of techniques for pushing people towards good policies. So if you've read the book Nudge or heard about the book Nudge, these are behavioral economists who are trying to use behaviorist techniques to improve how people behave as a society. But now what's happening is that the human-computer interaction field has kind of also adopted these techniques and wrapped them into these apps and web services that we're using. And it's called now typically persuasive technology, following BJ Fogg from Stanford, who has a huge lab that has developed these. And this book here, Persuasive Technology, is considered a Bible. Many of his students have later went on and started apps. For example, if I'm not mistaken, Instagram has started. He was a student of BJ Fogg. So all these techniques are now being used by app developers, by web developers in these big platforms. So now we have prediction and we have behavior modification. And then the question happens, what happens when you bring them together and the same organization has capability to do both, which I think is kind of new. There's a very interesting book from 2019 by Shoshana Zuboff, who's a psychologist at Harvard. And the book is called The Age of Surveillance Capitalism. And she has this very interesting picture in there, which I put on my slide. And this is the data, the behavioral big data that is being collected by, let's say, a platform like Google or Facebook. And the very bottom of it is the behavioral data that's being used internally for their own needs, for improving the services and so forth. The bigger part at the top is what's called surplus. And that's all the behavioral big data that these platforms use, not for internal usages, but instead they wrap them up, create what's called prediction products, like what I showed you before that Google is now selling to advertisers. And then they sell these prediction products in what's called behavioral futures markets. So now these platforms, actually the bigger use of their behavioral big data is to create prediction products and sell them to their customers. And these can be, again, marketers, insurers, political consulting firms, police or other kind of security forces, anybody who wants predictions about users. And when I read this very thick book, it's worth going through it. It's a long book, but it's very interesting. I was thinking to myself, hold on a minute. I'm kind of thinking myself as a, as a statistician, as a data scientist. And I said, wait a minute. So if predictions are now very valuable, the better your predictions are, the more value this prediction product is, you're going to try and make those predictions as accurate as you can, right? That's the goal. So we said, okay, how would you do that? We have all our traditional ways, what we talked about before, create better predictive models, get better data, improve your computing infrastructure, and we talked about that. But then all of a sudden, something very alarming came to my mind, thinking about knowing how these algorithms work. And I said to myself, actually, there's one more potential way that the predictions can look much better than without it. And that is, once you generate a prediction, you can actually modify and push the user's behaviors towards their prediction. So you end up with a prediction that's very close to the actual behavior. And that sounds like cheating because, again, as an academic who devises predictive algorithms, that's cheating, right? But let me show you what happens here and why this actually might be happening and so forth. So I'll give you two imaginary scenarios. Imaginary scenario one, suppose we have a political consulting firm, and this firm wants to reach out to citizens or people who are likely to vote for some candidates. Let's call this candidate T. And now you have an internet platform who wants to sell these predicted vote for T scores. So what the internet platform is going to do is they want to showcase their predictive power so that the political consulting firm buys their scores. So they're going to do two things. They're going to grab a bunch of their users and generate some vote for T predicted scores. And then they're going to try and push their users' behaviors towards their predicted scores, because once they do that, they will get pretty good results. So for the users who were very likely to vote for T, the internet platform can use behavior modification to push their behaviors towards voting to T so that they're more likely to vote for T. And for those who had very low scores, they'll try and push them lower and lower so that they really don't vote for T. And at the end, when you look at how well they did, we find that the platform turned these voting predictions into voting realities. Let me give you another imaginary scenario. So scenario two is I have an insurance company, and this insurance company wants to acquire new customers, but they really don't want high-risk customers, right? Because they want the good customers who only pay the premiums and don't have accidents. So they go and they want to buy these predictions from an internet platform, and the platform wants to sell them these predicted risk scores. The platform's going to do two things. First, it's going to take a bunch of users, generate risk scores based on all the behavioral big data that they have, and then they're going to modify the behavior of these users so that people with high risk will be more risky. For example, while they're driving, maybe you engage them on their app. Whereas people who had very low risk scores, they would try and move them away for any possible risky behavior, maybe not showing them things that they should not be seeing. And eventually, again, the platform will turn these high risk scores into high risk realities. So at this point, you're kind of thinking this sounds very dystopian. This is very weird. So let me just summarize, first of all, how it will work, and then we'll talk about why it would work. So this is a two-step thing. The platform can show that it improves its prediction in two ways, two steps. Step one, they generate predictions for a bunch of their users. They use their behavioral big data, they create predictive models, they generate predictions. Second step, once you have the predictions, you push the users towards their predicted scores using behavior modification. And the result of this will be that the predictions will look very good. And that's why I keep putting these quotes around improving prediction. So here was the picture that I showed you before about the statistical or machine learning approach to improving prediction. Now let me show you this other approach, which brings in the behavior modification and how that plays in. So right now, if I bring in the user has some kind of a mental state that will lead to their observed user behavior. The approach of the behavior modification scientist, if you want, or practitioner, is to take the platform and manipulate the platform behavior so that it impacts the user's mental state, which in turn pushes the user's behavior towards the predicted behavior. So remember, this is a predictable direction. And the result is that your prediction error is a lot smaller now. So things look very good, much better than had you not done the behavior modification. Now, you might, again, be asking yourself, why would a platform do this? And that was the first thing that I was a little bit alarmed about is, wait a minute, is this kind of against their incentives or why would a platform do this? So I started reading literature and looking at other places, and I found some very interesting clues in other places. So one area that has looked at this is media studies. And in a very interesting book called Team Human, media theorist Douglas Rushkoff writes, the better the platform does at making Mary conform to her algorithmically determined destiny, the more the platform can boast both its predictive accuracy and its ability to induce behavior change. So this is already one approach that's saying the platform they show their strength by doing this. In a totally different field, you find Professor Frank Pascal, who's a law professor at University of Maryland, and he wrote a book called The Black Box Society. And in an interview with The Intercept, he told them the following. He said, Facebook's behavioral prediction work is eerie, and he worries how the company could turn algorithmic predictions into self-fulfilling prophecies, since once they've made this prediction, they have a financial interest in making it true. So if you're thinking about what I just showed you now, showing that the prediction is accurate is very valuable for the prediction products. And then even if you go into the AI and you go and read Stuart Russell's book, he's an expert computer scientist at Berkeley, he says the following: content selection algorithms on social media are designed to maximize click-through. The solution is simply to present items that the user likes to click on, right? Wrong. The solution is to change the user's preferences so that they become more predictable. So this is even well known to the people who are designing. We're looking at the very technical people, to the legal people, to the people who are analyzing the media. And they all are basically saying, look, a platform has the financial incentive and the technical capability to do this. I gave this talk in a few places, and I let people read this, and some people just have the reaction, but tell me, are platforms really doing this? Well, my answer is, I don't have any evidence. There's no way I can have evidence. I'm not working at one of these platforms. I can't look at their algorithms and exactly see what they're doing. But I think that as a data scientist, I can tell you it's likely happening, perhaps inadvertently. Why do I think it's happening? It's happening because these platforms are using reinforcement learning now. And reinforcement learning, the way they use it, combines prediction and behavior modification. Now, I don't know how much you know about reinforcement learning. Again, this is a relatively newer field for me as well. But machine learning has basically three big areas. One is supervised learning, one is unsupervised learning, and the third one is reinforcement learning. But reinforcement learning is kind of different because reinforcement learning also builds in the user feedback. Whereas supervised and unsupervised are more passive. You have data from the users or from observations, and then you build your models. In reinforcement learning, it's more of a feedback thing that's going on. So if you search for reinforcement learning and you look at textbooks or videos or whatever it is, you'll see that the main kind of application where it shows up is in games. So for example, you want to teach an agent, a software agent, to play chess or to play Go or to play some very complex kind of game. And you have the agent and you consider the game as the environment, and the agent is trying to learn its environment. And this is set up as some kind of a Markov chain. So you have a set of states, and then the agent can take an action within a finite set of actions. And based on the action, it will receive a reward from the environment. And based on the rewards, it will keep taking actions and finally figure out what is the optimal way to play a game. So again, this sounds pretty innocuous and pretty cool and smart, but when you think about how platforms are using reinforcement learning, it's taking this to a second level. The environment in that case is actually the user. So the user is the environment, and the agent is trying to learn what the user's reaction are going to be. I just picked up a little nice diagram from an ICML paper, 2019 paper, that's called Generative Adversarial User Model for Reinforcement Learning-Based Recommendation Systems. And you can see here that the user is basically the environment. And this is about serving articles, if you want to think about Facebook and showing them news articles or whatever it is. And you have the different states. which are, what kind of choices the user made before, and you have the actions, which are which possible articles you can serve to it, and then the rewards are what the actually after you show the user a news article, whether they click on it, how long they stay on it, or whatever it is. So now really this reinforcement learning is built where the environment is the user. And the other really important part here is that reinforcement learning today is also combined a lot with deep learning to use predictions. So if you're familiar with, I don't know, control theory, if you're doing things like control systems, right, such as thermostats, right, where they turn on and off depending on the environment's temperature, you don't do predictions there. There you have a sensor and you just see what's happening, and according to what's happening, you change the behavior of the agent. But here you're adding prediction into it. And I'll show you just a very generic type of loss function that's being used here. You see that it has two parts. It has a target and it has a prediction. So deep learning is used to generate predictions of what the user is going to do next. And then we're trying to maximize this square difference between the target and the prediction. So with this setup in mind, even if the platform didn't have any malicious reason to do it up front, if they're using reinforcement learning, this is very likely to actually be happening. So now let me make an assumption that, let's assume that this is happening. And if this is happening, then there's a bunch of questions that we want to ask. So here are a bunch of questions that I want to share with you today. So one question is, can behavior modification mask poor prediction? So suppose that the platform is not really good at predicting your behavior, but can they use behavior modification to mask this and sort of sell their product to the customer to appear that they're actually doing very well? This is problematic because if then the customer is going to be taking these predictions and using them offline in a different system, or using them without this behavior modification later on, they're going to get a whole different type of predictive accuracy. A second question that I might want to ask is, can these customers infer the real predictive performance? So if I'm Google and you're an insurance company and I say, oh, look, here's the predictive accuracy that I have for you, and you don't see the predictive performance without my manipulations, this specific manipulation, can you infer what it would be? A third question that I got from a colleague at NYU, Foster Provost, was, how about if the customer does routine A/B testing on this platform? Because a lot of the advertisers will be doing A/B testing on Facebook or whatever. Can they detect this scheme that I'm doing? And the last question I want to ask is, what is the role of personalization in this special kind of strategy where you're both predicting and modifying behavior? So I'm going to try and answer these 4 questions. And to answer these 4 questions, what I want to do is I want to represent this new scenario that includes not only prediction, but also manipulation. And the next thing I want to do is I want to derive the expected prediction error under this manipulation. And expected prediction error, if you're a machine learner, this is, kind of the classic thing that's useful to do. If you're not a machine learner, then this is how you basically are able to look at trade-offs between bias and variance and identify sources of problems with predictive systems. So what I want to do, this is the expected prediction error. It's basically the expected value of the square difference between, typically it's the outcome and the prediction. But in this case, I don't want just the ordinary outcome. I want the manipulated outcome. So I want that, if you remember those 2 circles, I want the manipulated circle and the prediction. And I want to see how far they are from each other. I want to take this squared deviation and break it down into its components. The problem is that when I tried to do this, I had trouble because there's actually no notation for this manipulation that I can use in a way that's typically used in machine learning for EPE, for expected prediction error. So you have a world of prediction that has its own notation. You have a world for causal that has different notation, but there's no notation that you can actually put things together. And I'll show you what I mean. So what I tried to do is the following. I started with a predictive notation. This is the typical notation, standard notation. So for example, here you see if there's no manipulation, my outcome y conditional on x is some function f of x plus some noise epsilon. And epsilon has a mean of 0 and some variance sigma square. And I'm going to estimate this f somehow from the data, and that will be my predictive model. And f hat of x will give me my predicted outcomes y hat. This is all standard. Now the next thing that I need is I need the manipulated y. So for manipulated y, I need to somehow convey that this is manipulated. It's not just observed data. And for this, I'm going to borrow Judea Pearl's do operator. And Judea Pearl is a very well-known computer scientist who won the Turing Award. And he wrote this book called Causality, which is not an easy book to read, where he basically introduces this operator called do. So for example, you can see I have a do of b. B is some random variable, but if you put it inside of a do operator, it means that you are intervening on it, as opposed to x here that doesn't have a do. So x is just I'm observing that information, and b is I am manipulating that information. And this turns out to be a very important operator because it helps me distinguish between what I'm just observing and what I can manipulate. The next thing I did is, just to make things a little more easy, is I use this tilde notation. So y tilde, the little squiggly on top there, is going to be defined as my manipulated outcome, the user's manipulated outcome, which is the outcome given do of b. So this is how the platform manipulates its behavior. And x is just the input behavioral big data of this person. And this can be written as a function g. It doesn't have to be f. It could be some other function g of do of b and x. And I have noise. And now I'm using this tilde also on the epsilon because the noise also might have a totally different structure. So even if I have a mean of 0, I will have a variance of epsilon tilde that is some kind of sigma squared tilde. And once I put these two together, then I can do something pretty cool. I can combine them and then look at the quantity of interest, which is this y tilde minus y hat. Okay, so this is the difference between the manipulated y and the predicted y. If you remember my little graphic from before, you can see at the bottom now where the do comes in. So on the right-hand side, I have the manipulated platform. So the do b is the platform's manipulated behavior. So this is manipulating the platform's behavior, which in turn manipulates the user's mental state, which leads to this tilde here in the green circle. So now what we're going to try and break down is this prediction error between the manipulated y tilde and the y hat. The classic expected prediction error formula, if there's no manipulation, the ordinary thing, if you just search it online or if you haven't seen this before, this is the classic bias variance breakdown. And we break down the expected prediction error into 3 pieces. One is just noise, that's the sigma square. Then we have the bias of the predictive algorithm. And then we have the variance, which is due to a limited sample size. And what I did in the paper, which is an archive, I'll share the link at the end, is I did the same breakdown for the manipulated y. And what I get is a formula that looks somewhat similar, but somewhat different than the no manipulation case. So if you compare these two formulas, you'll see that there are 2 interesting new things that show up here. One is, first of all, the variance is the same thing. So it means that if you have a larger sample size, your prediction error will be smaller. That's good news. That's nothing surprising. The second part here is the bias. But the bias here has an additional piece called CATE, or Conditional Average Treatment Effect. And this is basically the average magnitude of the behavior modification on a person who has a profile X. What this means is that if this CATE here has a sign that's opposite of the bias. So if bias is 3 and CATE is -3, you've actually removed the bias. Now, CATE doesn't have to be exactly minus of the bias. As long as it has the opposite sign and this shrinks down this squared combined term, you have a way to shrink the bias term, which is very powerful. And the third piece here on the left is this sigma tilde square, which means that in this new scheme, you can actually also manipulate the noise. So the difference between people who have the exact same profile X can actually be worse or better if you do it properly. And I want to show you this formula here, or the effect of this formula, with a little graphical example. So let's assume that we're talking about this platform that's a food delivery platform. Okay, choose your favorite one. I don't know which you like to use, whether you use them. And let's say that this platform is going to be generating drivers' risk scores. So I'm going to build something very simple. Suppose that I'm going to build a model of risk as a function of the trip distance. And the longer your distance, it's riskier. So there is, let's assume the true curve, which I don't know, is something that kind of goes up like this, okay, this curvilinear line here. And I'm going to be measuring risk by how long this driver is spending on their app during their driving. So if they're spending 80% of the time or 90%, whatever it is, it's more risky. The other thing you see here are these circles, and the circles are different drivers. So we see we have short distance at x1. We have a bunch of drivers there with different risk levels. And we have medium distance, x2. And we have long distance, which is x3. Okay, so this is the true function, f of x. I don't know it. What I'm going to try and do is I'm going to try and approximate it somehow. So I'm going to approximate it, say, with just a linear line. And suppose that I have a ton of data, so forget about variance for now. Let's keep it simple. And now that what I see here are these red x's. If you see over on x1, I have a red x. And for x2, I have a red x. And for x3, these are my predictions based on my predictive model. For the short distance, there's no bias. I'm exactly fine. On average, I'm perfect. But for the medium distance people, you see that my predictions are too high. In other words, my predictive model has a negative bias. And for the long distance, I have a positive bias. My prediction is too low. So now I can actually, if I'm the platform, I can use behavior modification and start playing with the risk of these drivers, right? I can engage them, I can send them through longer routes, I can do all kinds of interesting things. So suppose that here is how I modify them. So people who go on short distances, I'm not changing them because that was fine. But for the drivers who are driving medium distances, remember that my prediction was a little bit too high. So now what I'm doing is I'm pushing their risk. I'm making their driving a little bit more risky so that their prediction now looks much better, right? They're now closer to the prediction. And for the people who are driving long distances, I'm actually lowering their risks by using behavior modification. This is one kind of a behavior modification. But if I do it even better, then here's another take on this. What if I'm now doing a behavior modification that doesn't only shift up or down by the bias, but also can stretch or shrink? So now the yellow dots here are a behavior modification that not only shifts up or down, but also shrinks the driver's risks closer towards the prediction. So now I have drivers that are not only closer to the prediction, but they're also closer in terms of the risk to each other. And that was that sigma square tilde that I was showing you on the previous slide. Okay, so now that we have this nice EPE, this nice breakdown, I can start answering the questions that I had before. So the first question was, can behavior modification mask poor predictions? And the answer is yes, definitely. Remember this little Kate in here? That can definitely go ahead and reduce the bias. And I can also play with a sigma square tilde, and that can reduce the error variability. So I don't need to predict very well as long as I do my behavior modification properly. My second question was, can the customer infer the real predictive performance? And the answer is not likely, because in order to, if you look at these two formulas with and without the modification, it includes terms like Kate and bias and sigma square and sigma tilde square. Even if you're the platform, some of these are nearly impossible to estimate. So a customer is really not likely to be able to capture these. The third interesting question was, if the customer is doing routine A/B testing, can they detect this scheme that I'm doing? And the answer is no, because if you're doing A/B testing, you're randomly assigning customers to A and to B. So my little devious plan is being randomized across the A and B equally. And by comparing them, you won't see any difference between them. So it's actually masking my do operations. And finally, the fourth question was, what's the role of personalization here? And what's interesting is that it plays a dual role. First of all, you use it for personalizing the predictions. So the better you can predict, you're not going to have to modify that much. And the second one is you can personalize the behavior modification. So I can personalize the content, I can personalize the design using things like website morphing, and I can also personalize the type of reinforcement that I give you. So maybe you're more susceptible to social pressure and someone else is more susceptible to time pressure. I can use these different kind of personalizations in terms of the behavior modification, so that if I better modify you in a personalized way, I get a better prediction product. So finally, I mean, I've shown you how we're actually, this kind of strategy might be tricking the customers, but let's not forget about the users. So although behavior modification is not an evil thing, it came out of psychology, it was aimed at helping people improve their lives and improving society. What's happening now is that the use here is that it's making users conform their algorithmically determined destiny or predictions without our knowledge or consent, in order to optimize the platform's commercial interest. And usually, as I could, you could definitely see that making people more risky is obviously not to the well-being and agency of humans. So what I tried to do is to show you that with a statistical approach, I can actually uncover some of the implications of this strategy, whether or not it is happening. And to just summarize, the internet platforms now combine both of these capabilities, which is what's new and creating this strange possible strategy. The imaginary scenarios I showed you, maybe they're not so imaginary. And the approach is kind of absent from our literature because we don't typically do both behavior modification and prediction in the same communities. We have two separate communities that do both of them and analyze things separately, but now the companies are able to combine them together, and we're getting some really interesting and somewhat worrisome results. I had to introduce this new technical vocabulary in order to put them together and do the analysis. And once I did this, I think this is useful not only for EPE, but there are also a lot of other strategies that combine prediction and manipulation. And if you look at papers such as about uplift modeling, they're very clunky, they're very weird because they don't have the appropriate notation. So the bottom line is there's new notation. We're able to uncover some implications for the platform customers and users. And I hope that I convince you that something interesting is going on here. So I'll close here so that we have some time for comments and questions. Thank you very much.
Thank you, Galit, for the very insightful presentation on predict and manipulate. And as you said, we are going to open the floor for questions. So I suggest that whoever has a question, please raise the hand, which is one of the options here. So we have a question from Jimmy. If you could, show your video, that would be nice for Galit.
Yeah, of course. Let me see if it's working now. Is it okay now, Galit? Can you see me?
Yes. Hi, Jimmy. Sure.
Hi, Galit. I've been listening delightfully your presentation here. So a few things. My background is experimental economics. So the questions that I'm going to or the comments that I'm going to say, it's related to that, right? So I've been coming to the machine learning literature from the experimental perspective, right? So when you talk about Kate and conditional average treatment effect, it speaks to me in a way, right? So the things that I was having in mind is how you can test this with the tools that we have, right? So the first thing that came to my mind is that if you want to test this hypothesis, you will not get any of the companies doing these behavioral modifications to go along with you, right? I was thinking about two ways. One is maybe find a natural event, a natural experiment in which, for example, social media was shut down, and see if the behavior modification is not going on, right? To identify your treatment effect. That's one natural event. The other way that you can test this is possibly with experiments where you identify, for example, a behavioral modification tool, and then you have a control group that you want to predict something, and then you have another group in which you have this behavioral modification and figure out if prediction actually goes on, right? So I was thinking that if there is something along those lines that has been done before in the literature, do you know anything about this?
Thanks, Jimmy. I think this is a great question, and I think the problem is that in order to do a randomized experiment, for example, right, or even a natural experiment to have one, you need to be able to have the users who are affected by this scheme. You need to know who they are so that you can partition them and say, here are the ones who are getting the behavior modification, here are the ones who are not. Unless they are identified to you, there's no way for you to know who is in which group. So the problem is going to be that if you're doing reinforcement learning, you're going to have to separate all the behavioral big data and say, okay, so now the reinforcement learning is turned off. I mean, you need the platform to agree to turn off the reinforcement learning. I think that's going to be pretty tricky. But I think, you know, this is interesting because David Martins and I and a student of mine, Travis Green, we recently wrote a paper talking about how when you have the platforms doing reinforcement learning, we have a problem as researchers that don't have access to turn it on and off and do experiments on it. Because once it's running in the background, you really can't do anything. Everything that you try and do, it's all, you know, you can't parse out the causality. So I think you're raising a very serious problem that I think unless you have your own platform that will allow you to try to turn off the reinforcement learning and not touch some of your users, I just don't see how to do it.
But can I say something? This is where experiments in the lab can actually become handy, because you can identify one little behavioral manipulation tool, right, and use it in your experiment to predict behavior, to see if it improves your prediction. Let me give you an example. I have some friends that they run experiments here in Denmark where they were testing some hypotheses about gambling, right? So they created this software that will simulate gambling techniques like the near misses, where you have something that was close to 7 and then 7, so people say, oh damn it, I almost got it. Or they use the clink 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 sounds to get people hooked into this, right? And they found out that these techniques that they use in gambling casinos, right, they actually change risk preferences. So if one can identify a particular behavioral modification technique that they use in social media, and we replicate it in the lab, and then we ask people to do some choices. Then in the control group, you don't give them the manipulation treatment, and then in the other one, you give them a manipulation treatment, and then we can see if there is a causality on the predictive error, right? And
yeah,
then,
that would be very cool. In a lab, if you can set this up in a lab, I agree. That's the only way where you have control over what's going on.
Yeah, the other question that I had is, maybe this is one thing or one area where regulation can actually make something, because then you can ask people, well, if we have researchers that wants to study this, then you, a company, you have to allow the researchers, whoever they are, to turn on and off these behavior modification techniques, right? Imagine that some supervisory agent it's smelling some of these things going on, and then you send to a company and say, well, now we are going to test if you are actually doing this, right? So then you have to turn on and off. Yeah. Anyway, but that's I thought it was maybe a area where regulation can do something about.
It would be amazing. But I really like your idea of trying to create even a very simplified version of this in the lab. I think that would be very useful, because right now, you know, I'm just getting a lot of disbelief. It's like, no, it's impossible, yes. But it's possible, you know. Yeah.
Maybe we should talk more about it.
Okay, great. Thank you.
Yeah.
Thank you so much, Jimmy. We have another question from David. If you could turn on your video so that Galit,
I'm trying to do so. Okay.
Hi, David.
Thank you hello, Galit. Thank you. Thanks for the very nice talk. And sorry for interrupting, but I wasn't seeing the slides. It was frustrating, but then I finally solved it. So I have one question regarding the last part of your talk, the example on the riders for food delivery. So I can more or less see how you could act on the bias. I mean, you mentioned how, right? I mean, you could let the riders engage more or less with the app by sending them messages, and then you could change the risk exposure. But I don't quite see that example how you could act on the sigma. I mean, how can you shrink the deviation? Could you perhaps provide an example on how this thing could be done? Thank you.
Yeah. So great. So the way to shrink the sigma is if you can personalize the behavior modification. So if some of these users, you know that they are more susceptible to noises, and the other one, I don't know what it is, you know, but if you're able to personalize the behavior modification, then you push people in the right direction in a better way.
Okay, I see. Okay. Thank you.
Sure, thank you. Since I don't see Dolores, maybe, yeah, please go ahead.
Should I?
Yeah, go ahead, please.
Thank you. First, thanks for a truly excellent talk. I'm wondering, though, since you point out that this is largely absent from the statistics and machine learning literature, which is my impression too, how can one bring it more to the center? I mean, the whole debacle around Timnit Gebru's departure from Google points to the fact that these platforms obviously aren't very motivated to focus on these issues. And a lot of us see that they are important questions to pose, but how can the research community make them more of a focus?
Well, look, it's a difficult question. It's a great question. I think the first thing is I'm finding trouble even getting our own research communities to try and believe me. You know, publishing a paper like this, you won't believe how hard this is. Because they say we want to see evidence that this is happening at a platform, which is of course impossible. So I think in order to open up these kinds of debates, first of all, our research community needs to be open to things like this. Then there's another issue, which is there's a lot of, I feel there's some groups that are very invested in their own, methodologies. And for example, taking, you know, Pearl's do operator and putting it together with prediction stuff, that is causing some people to be not happy. Because, you know, I could have chosen something else. It's kind of, in my opinion, I don't really care what it is, as long as it works, it works. But I think that there's also an issue of people very married to the traditional ways of doing things. So it's a good question. My answer to you is I'm giving lots of talks about this in lots of different audiences, hoping that this will raise something. But your question is a really good question.
Because I think you're touching on part of the problem in how to get results that are kind of undisputedly publishable. I think you've done an excellent job here in formalizing this in a very clear and good way. But it's kind of making the steps further towards, because I think researchers are generally well-intentioned or interested in these kind of critical perspectives too, but researchers are motivated a lot by what they can publish. And it strikes me that this might be a hard field to kind of incentivize by publication points, basically.
Yeah, I agree. And I think Jimmy's point about trying to show this in a lab, maybe that will be a breakthrough. I'm not sure, but I agree with you. I think that's why when I started my talk, I said, I'm going to describe something that's a little unusual, but I don't even know how to describe it to you. So let me just describe it to you. But I agree with you. This is tough, but I think we should keep having, you know, focusing on these big pictures, even if it's not like the immediate traditional way of doing things. And again, giving talks is probably the way to just get the word out about it and get more people working about it and thinking about it. So, you know, if a lot of different people start working and figuring this out, then it won't be so unusual anymore.
Galit, may I say something? Can I jump in? Very
Jimmy,
quick.
Sure.
Yeah.
Okay, very short, because we have another question and we are over.
Okay, no, then I just a question, and then if there is time,
yeah.
I say, yeah.
Yeah. Emmanuel, you have a question if you would like to show your video.
Yes, thank you very much, Dolores, for arranging this, and of course, many thanks to Galit for her fascinating talk. I just wanted to throw in probably two elementary thoughts according to these very important questions. One is the temporal aspect. You're talking, and it was very clear about time series, about dynamic, about processes. Actually, the way you framed it, it's probably also the historically correct and observed way is that the platforms are responding to the new to their new possibilities after having
It's frozen.
Emmanuel, I think you are frozen. Okay, so we got the temporal aspect. Yeah, so he's trying to join again, I think.
I'm fine to stay a little longer, so no worries. If people want to ask questions, I have no problem.
Yes, and I think, yeah, I think I can see that people are very keen on staying. We have another question. Emmanuel, please go ahead. I think you are now connected again.
Do you still have the word? Sorry for that.
No worries, no worries. So please go ahead.
Okay, so I was talking about dynamics. So it's a process and it can be repeated. And I'm also thinking about responses. So the association which came to my mind is, of course, a very old-fashioned one, is game theory. So we're not talking about any moving targets, but we are talking about equilibria. I would be interested in, oh, Galit has left?
No, I'm here. I'm here.
Okay.
Yeah. Right.
So yes. I would be interested in your view about your perspectives, how equilibrium considerations, and we're also talking about regulations and about trying to control in a very general sense these very real. I see the threats, but we can also just see that as a real process which we have to cope with. So what would be your view on that?
So, okay, so I'm no expert on game theory, and I would be very interested in finding out, what is different in the formulations. But a few things that I can point out. First of all, they're not just two parties here. There is one party that's the platform that's just using an algorithm. So the platform doesn't even have an intention, if you want to think about it. They're just minimizing some loss function, right? And then you have many, many, many users, and it's not a one-shot thing. So this is a game that keeps going on more and more and more and more. So you push the user and you generate a new prediction and another one. And also in game theory, I think you're not generating predictions in the way that they are, because they're using a lot of other information. So I think it's more complex, just the whole prediction process that's going on in there. I think there's also a lot more asymmetry than you have in game theory, unless you can convey the same asymmetry. I think the user doesn't even know that they're being manipulated, and most of the times we're not even aware of it. And even when we're aware of it, there's nothing we can really do against it, right? Because that's the biggest problem, that we're not able to exercise our agency. But I think it's a great question to ask, how does this differ from a game theoretical formulation? I think that's a really great question. And when you put in a new formulation, the main question you want to ask, how is this different from other ones? And people have asked me other questions, but I have not heard the question about game theory. So I would definitely need to think about that. And if you have thoughts about that, I'd love to follow up in here. That would be great.
Thank you. Just the one last remark is, we had this from natural scientists had this similar problem 100 years ago about the influence of measurements. So before there was a paradigm that you have an objective measurement. We have to forget this since more than 100 years due to Heisenberg at the latest. So this is, I think, a quite similar situation. Of course, there are practical solutions to that. Nobody uses quantum mechanics for everyday macroscopic measurements still. And this will be there were concerns expressed about publishable work and impact in everyday society, in general society. But nevertheless, although there was good practice before quantum mechanics, in the end, this is now common knowledge. And in the same way, I'm convinced that your approach, or the approach of manipulation and prediction, the interaction will in the medium run survive and get more impact even on the, not only on the scientific level but also on the societal level. So sorry for my long statement.
Thank you.
Thank you so much, Emmanuel. Davide, you have raised your hand.
Yes. Hello. Thank you very much for your seminar. It was really, really interesting, and I think you really nailed the point, because what are the things that you are saying are very likely. I think they do not seem fantasy. And now, going to my question, you say that platforms now use reinforcement learning that combines prediction and behavior modification. But I wanted to know what is the reward in the reinforcement learning technique that social media uses to make me more likely to do a choice or to optimize my inadvertently, because I don't know that I'm optimizing my my choices, but I wanted to know what is the reward for me using the social media to go through a choice that the social media wants me to do.
Thanks, Davide. So this is the interesting, tricky part. The rewards are not what you get. The rewards are what the system gets for guessing you correctly. So every time they show you, you know, the right news post and you spend enough time reading it, or you click on it, it gives the agent, the software agent, a reward. So they know, oh yes, we did the right thing. Or if they showed you something and you just, oh, this is useless, and you just ignore it, then they get a negative reward or something like that. So the whole wording here is kind of funny, because usually we're not the environment that's being explored, but we have to sort of think of ourselves as the environment.
Yes. Okay, in this case, then, aren't they tricking themselves a bit? Because if they are doing bad predictions, but then they do good predictions because they modify our behaviors, and they get the reward for because I choose a product from a bad prediction. Aren't they giving themselves a reward for a bad prediction? Isn't sort of tricking themselves, and so they are not seeing how they are not really optimizing their predictive power?
Yes, in fact, that's what's happening. They're not improving their predictions in any way. They're just minimizing the prediction error. And minimizing a prediction error, yeah, exactly what you're saying. And that's why the title of this talk has a big quotes around improving, which some people, you know, miss that, but that's the whole point.
Okay.
Yes.
It's not even important at this point if they are improving their prediction or not. Okay.
Well, if they improve it, then they need to modify you less. So if their prediction is better, then there's less modification that's needed.
Yes.
Okay. Thank you so much. Yeah.
Thank you very much.
Thank you very much, David.
Thank you.
I think we, Jimmy, your hand is up, but do you have any comment? Otherwise, we are about to close. Because,
yeah, I have a suggestion to think about it this way. I think I can say it in 1 minute. So Galit, I think the argument that you're making, I believe it. If I have time, I will explain why. But maybe the argument is from an industrial organization point of view, right? Imagine a company, right, that has two options. One is to go in the business of prediction only, right, to invest everything into predictive analytics and so on, and the other one is a combination of owning some prediction data company and then a behavioral modification platform, right? So what I'm thinking is that the profit maximizing strategy is to choose the latter, because then you don't need to spend a lot on predictive, but more on behavioral modification platforms, right? So because what you're doing there is just one part of the equation of the company, which is reducing prediction, right? But one would probably, if you embed that into a profit maximization framework, then you naturally it will arise in the decision of the firm to go for a combination of predictive analytics and behavioral data collection and behavioral modification platforms, right?
Yes, and I think that's exactly why they evolved to do it, for sure.
Yes, yeah.
Thank you very much, Jimmy. And Galit, you have seen that you have attracted a lot of attention, and there will be even more views in our YouTube channels. So we all, the audience here, but also the one that we will get later, would like to thank you for your very insightful presentation.
Thank you. And I wanted to just mention there's a paper on archive if you want to see it. And if you want to continue the conversation, feel free to email me. My email is very easy. Just type my name and you'll find me. Super easy.
And if we don't have it already on the website of the online seminar series, we can add the link to the paper that we have
Super.
done with other, so that the people can refer to that. Okay, thank you again, and talk to you soon. And for the rest of the audience, we will be back to 4:30 next week, usual time. Thank you.
Thank you very much.
Thank you, Galit.